In this video, we are going to talk about data integration and preparation. For most people, they think data integration is a very technical topic, something that's only for IT department to worry about. By the end of this video, I hope you will understand why that thinking is incorrect, and that may cost companies hundreds of millions of dollars. Let me start with a story. It was October 1999. Picture you are a senior executive at one of America's most iconic candy companies. Your warehouse are stacked floor to ceiling with product. The retailers are begging for inventory. The kids are waiting. The Halloween, which is the biggest sale of candy of the year, is just weeks away. However, you cannot ship a single piece of candy. Not because of labor strike, not because of supplier problem, not because of quality issue. The candy is right there. The trucks are ready, but your systems, they completely collapsed. So what actually happened? What went wrong at Hershey in 1999? So earlier that year, the leadership at Hershey made what seemed like a very smart decision. They tried to modernize everything at once. New SAP system for enterprise planning, new Manugistic for supply chain, new Siebel for customer management. And here is the first mistake happened. A project in this complex, integrating 3 major enterprise systems, normally takes 4 years or 5 years of careful planning and testing. But 1999 was a year everyone was terrified of Y2K. Remember that? The fear that computers would crash when the calendar hit 2000. So the Hershey's leadership said, we need to get this done faster. They compressed the timeline to only 30 months. Then came the fatal decision. They went live in July. Think about that for a second. If you sell candy, when's your most critical time of the year? Halloween through Christmas. And they choose to flip the switch on their entire technology infrastructure 3 months before the peak season. So when orders started flooding in, the system couldn't handle it. The SAP system did not talk properly to Manugistic. The orders got stuck. Inventory data was wrong. Distribution could not figure out where to ship. So the result was not just embarrassing, it was disastrous. Over 100 million in orders they couldn't fulfill. Stock price dropped. Competitors like Mars and Nestle, they swooped in and took the shelf space. Now look at these boxes at the bottom of the slides. This is a lesson I want you to carry with you. Data integration is not just an IT project. It is not something that you delegate to the technology team and you forget about. When your system cannot talk to each other, the business stops, even when you have everything right. So let's connect this back to our course framework. You can see on the left-hand side, we have our data triad, the 3 concepts that we talked about earlier this semester. Decision support at the top, technology context, organizational context, and everything interconnected. Now let's look at the architecture stack on the right. Find data integration is highlighted in green there. See where it sits. It's right in the middle of everything. Below it, we have storage and data management. Above it, we have the query processing and analytics. So data integration is invisible when it works. Nobody thanks you for it. But when it fails, everything above it in that stack, all your analytics, your dashboard, your AI models, they become useless. It's like the foundation of a building. Nobody walks into a skyscraper and says, wow, what a beautiful foundation. But without the foundation, there's no building. So here's the agenda for today. First of all, we are going to understand why this problem exists in the first place. Why do we need data integration? Then we're gonna define our terms and look at some main approaches. After that, we will go deep on ETL, which is a traditional workhorse. And finally, data virtualization, which is a newer approach that's gaining grounding fast. So let's dig into the root cause. To understand why data integration is such a universal challenge, we first need to understand how companies are actually organized. Look at this departments lineup. We have purchasing, operations, accounting, finance, marketing, so on and so forth. This is a textbook organizational design, and this is also how most companies in the world are structured. And there is nothing wrong with it. When we group people by functions, that makes a lot of sense. Accountants learn from other accountants. Marketing people collaborate on campaigns. You get specialization, you get a clear reporting line, and you get very efficient training. But here is what the textbook don't tell us. When we organize people this way, the technology follows the same pattern. Think about how IT projects get funded. The marketing department has a budget and a problem. They need a management system, so they buy one, optimized for marketing. Similarly, accounting has a budget and a problem. They need better financial reporting, so they buy something optimized for accounting. In the real world, nobody wakes up one morning and decides that we're going to create data silos. But data silos happen organically. Each department tries to solve their own problem, but then we create one system at a time. I like to think of this as a restaurant with separate kitchen for every type of food. The grill station is perfect for steaks. The pasta station is perfect for Italian. Each kitchen runs beautifully on its own. But what happens when a customer orders steak with pasta? Now you need those kitchens to coordinate. But if they've never talked before, that's when orders get lost. And here is a foundational tension. So look at those horizontal bars cutting across the vertical silos. We have the procurement process doesn't live in one department. It touches supply chain, purchasing, production, finance, and we have the fulfillment process spans sales, inventory, warehouse, customer support. And this is just one example. Real business processes are horizontal, but our organizations and our systems are vertical. And in the middle, we have data sharing required. That is not a nice to have, that's a must to have. When a customer places an order, the sales department needs to see inventory. The warehouse needs shipping address. Accounting needs to generate invoice. Customer service needs order history. Every single one of these steps requires data to flow across departmental boundaries. And that's exactly where things break down. So on one side, there's smooth sailing within department. Within every department, the data flows beautifully. Systems are designed for that team's needs. Everyone speaks the same language, use the same definition, follow the same processes. On the other side, rough waters. Across the department, the moment data needs to cross a departmental boundary, everything gets harder. Different systems, different formats, different definitions. The customer ID that sales use, accounting may call something different. So the system excels at solving local operational issues, but fail at organizational coordination. Each department is locally optimized, but the organization as a whole is a mess. So here's an analogy I found useful. Imagine a neighborhood where every house has its very well-designed plumbing, beautiful and great water pressure, but there is no connection between houses, no city water main. Each house works perfectly in isolation, but try to coordinate anything, share water during a drought, or deal with a contamination issue, and suddenly you realize the whole neighborhood is just a collection of disconnected systems. That's most enterprises today. So here I have one example, just to illustrate the problem. Suppose that a customer places order with sales. Within the sales department, everything works great. The order flows into their IT system, gets recorded in their databases. Then we have the arrow to the left, smooth data sharing within the organization. Now that order needs to go to warehouse for fulfillment, and here is where reality hits. So the arrow between sales and the warehouse, the paperwork and phone call, they need to talk to other departments. In 1999, it was probably by fax. In 2024, maybe an email or Slack message. But the point is the same. There's no automatic system connection. Someone has to manually transfer that information. And what comes with manual handoffs? There is delays, errors, missing information. Then it happens again between warehouse and accounting. More manual handoffs, more delays, and more opportunity for mistakes. So now here's the thing. Hershey wasn't some backward company using paper ledgers. They had invested heavily in technology. The problem was not the lack of system, it was lack of integration between the systems. And if we look at the data flow of my previous example, then we can see that the data can flow very well within each department, but between departments, from sales to warehouse, there will be communication delays. Between warehouse to accounting, again, communication delays. Now imagine this is just one order, but thousands of orders. Every day, every handoff is a potential failure point. We talked about the delays and handoffs and the potential mistakes, but the problem does not stop there. When we have multiple systems, there may be data conflicts, and that's a more serious problem. So in this example, I have three very simple tables for a university. Student data, and probably from the registrar. Student employees, maybe from HR for students with campus jobs. And student health table from the health center. So every system was designed independently to serve its own department's needs. So everyone works perfectly fine on its own. But look at what would happen when we try to combine the three of them. So the first problem is that how do you even identify a student? In this example, student data use student number, but in student employee, they use student ID, and student health use student name as identifier. So think about that. Names are not unique. And the student ID and student number, are they the same thing? They could be the same, but we don't know, and they are named differently. And the second problem is that maybe we have the same concept, but we have different labels. And that's what we see with student number and student ID. And that's obviously the same thing, but they are named differently. So if you are writing code to merge these two tables, how do you know these fields actually match? You don't unless you manually check the meaning of every single column. The third problem is that we have different data structure. So the student health data stores the name as one single field. But if we look at student data, it breaks the name down into last name, middle name, and first name. And it's nice and clean. Smith R. Elaine with Elaine R. Smith. That is unnecessarily but surprisingly hard problem. The fourth problem here is conflicting data. So if we look at the student phone number in one system, so Smith in one system, we have phone number 283-4195. But now if we look at Smith's phone number in the student health data, and it's different. So which one is correct? We don't know. The fifth problem is missing data. So some insurance information is blank in student health data, and what happens if the student has a medical emergency? So please remember, this is one student across 3 systems. And in real enterprise, they may have millions of records across dozens of systems. The conflicts will multiply exponentially. At this point, some of you might think, okay, but what if we just design everything right from the very beginning? That's a very reasonable question. And the answer, however, is it doesn't matter. Even perfectly designed system needs integration eventually. Why is that? Because first of all, the systems age. What worked fine 5 years ago doesn't meet today's needs. The business grows, priorities change, technology evolves. Second, the organizations also change. Companies merge, they acquire competitors, they spin off divisions. Company A has their perfect system, but Company B have their perfect system. But now if you own both A and B, they have to talk to each other. So the bottom line here is the question is not about whether you will need data integration. It's about when and how. So we have now established the problem. Now let's talk about solutions. What exactly is data integration and what are our options? Let me give you a formal definition and then we will make it practical. Data integration is a set of practices, techniques, and tools that take data from different sources, such as internal systems, external partners, cloud services, and then combine all of them into a unified view that the business can actually use. Here's how I think about it. Imagine you are a translator at the United Nations. You've got delegates speaking Mandarin, Arabic, Spanish, French, German. Each language has its own grammar, its own idiom, its own way of expressing ideas. So your job isn't just word-for-word translation. It's making sure everyone understands the same message. And that's data integration. Sales can speak CRM, finance speaks ERP, marketing speaks campaign platforms. You're translating all of that into coherent language that business can use for decisions. So the market numbers are very high. We have 15 billion in 2024, projected to hit 47 billion by 2034. That's not a niche technical specialty. That's a massive growing industry. Companies are spending serious money on this because they've learned the hard way that what will happen if they don't. So there are 2 main ways to deliver integrated data. The first is physical delivery that moves data in bulk batches. That's what we call traditional ETL. The second is virtualized delivery, which accesses data in real time without moving the data. And that's a newer approach that we will explore later in this video. At a high level, we have 3 specific approaches. And understanding the differences of those 3 will help us choose the right tool for any situation. The first is data consolidation through ETL. In this approach, we physically extract data from source systems, transform them into some common format, and then load it into a central repository, usually a data warehouse. So think of this as building a central library. You gather all the data and all the books from everywhere, you catalog them using a standard system, and then organize them on shelves in one central building. It takes time, but when you're done, anyone can just walk in and find exactly what they need. The second approach is data federation. Instead of moving data, we create a virtual layer that makes separate datasets look similar, like one unified database. So when someone runs a query, the federation engine figures out what sources has the relevant data, pulls it just what's needed, and combines it on the fly. So going back to the library analogy, so instead of building one central library, we create a universal search catalog that knows the location of every book in every library across the city. The third one is data propagation, and this is event-driven. When something happens in one system, like a new order, a customer update, and that change automatically propagates to other systems. It's near real time, triggered by business events. So most large organizations use all three of them. The question is always which approach for which problem. So let's simplify into two fundamental philosophies. The first philosophy, move the data, and that is ETL. Extract it, clean it, transform it, put it somewhere central. The second philosophy is leave the data where it is. That's virtualization. Create abstraction layer that lets user access data as if it were in the same place. So here's a key insight. They are not competing approaches. They are complementary. So ETL gives us a stable, reliable, historical foundation. When the CFO needs consistent quarterly numbers, ETL delivers it. Virtualization gives us speed and flexibility. So when a business user needs to quickly answer an ad hoc question by combining data from 3 different systems, virtualization delivers. So the best data architecture really use both of them strategically. So now let's dig into ETL, the approach that's been powering data warehouse for 3 decades. So the 3 gears represent the 3 core operations: extract, transform, and load. Very simple concept, but very complex execution. So why does ETL requires new storage? Because we are building something organized for a different purpose than the source system. Your sales system is optimized for processing transactions first. Your data warehouse is optimized for running complex analytical queries, different purposes, different architectures. And we also need a bulk and a batch movement. And why? This is because of efficiency. Moving 1 million records at once is far more efficient than moving them one at a time. Most organizations run ETL jobs overnight. So that's 8-week setup time. Yes, that's real. ETL projects are not quick wins. You're mapping source schemas, defining transformation rules, handling edge cases, and testing extensively. So when it's done right, you have a single source of truth. One place everyone trusts for the official numbers. Now the challenger, data virtualization. And here the philosophy is fundamentally different. Instead of copying data to a new location, you create a logical view that makes distributed data accessible as if it were unified. So no data movement means no synchronization headaches. The data you are accessing is actual source data, not a copy that might be hours old. So real-time access means decisions can be based on current information. And that 1 week setup time compared to 8 weeks for ETL, that's a game changer for agile organizations. But there's also a trade-off. When you run virtualized queries, you're hitting the source system directly. Complex transformations, heavy queries, that can really bog down the operational system trying to run your business. So that's why virtualization is not a replacement for ETL. It's a complement. It's great for certain use cases, but not appropriate for others. So how do we choose? ETL shines when you have large data volumes needing complex transformation, when you need history consistency, when lots of users will run heavy analytical queries. On the other side, virtualization shines when you need speed to market real-life data, flexibility for ad hoc analysis. My advice is don't think of this as either or. Think of this as building a portfolio. The ETL for your foundation, the stable, trusted, historical data. Then virtualization for a flexibility layer, the quick answers, experiments. So now let's go deep on ETL. Understanding these mechanisms will really serve us well regardless of which tool you end up using. Here is the ETL pipeline visualized. On the left, we have our operational systems, and these are the database that runs our business. Then the dashed cylinder in the middle, that's our staging area. This is a temporary workspace. So think of this as a workshop where you bring raw materials before you process them. On the right side, we have this reconciled system, and this is our data warehouse. This is a finished product optimized for analysis. So the step 1, extract. This step, we pull the data out from the source systems into staging. The challenge here is doing it without disrupting operations. The second step is scrub and cleanse. So in staging, we fix data quality issues. We catch the misspelling, the impossible dates, and also the duplicates. And this is a dotted line because this is not officially an ETL process. This is a data preparation and data cleaning process. Then we move to transformation. Transformation is about reshaping the data for analytical use. So we convert currencies, aggregate transactions, join records from different sources. The last step is load the data and index the data. Here we will move the finished data into the warehouse and we will build indexes so queries can run very fast. ETL is typically a repeating cycle. Now let's add some nuance to each stage. Extraction is about capturing data without alteration. You're taking a snapshot, you're not changing anything yet. The key challenge is to minimize the impact on the source systems. Cleansing is where data quality getting reinforced. Think of this as a quality control checkpoint. The records that fail validation might go to expression queues for manual review. Transformation is where the real intellectual work happens. You need to understand both the source systems and the analytical requirements. So what does this field mean? How does it map to the warehouse schema? We need to figure that out in transformation stage. I often compare transformation to cooking. Extraction is gathering ingredients. Cleansing is washing and prepping them. Transformation is actual cooking, combining, reducing, and seasoning. And loading, these sound simple, but has real complexity. Full loads versus incremental. What happens if it fails halfway through? These are all the decisions we have to make. So now let's move further into each of those steps. Extraction seems straightforward, but there are real decisions. So what to capture? We typically don't extract everything, but then which table matter? Which field do we actually need? Then when do you capture? Real-time extraction give you current data, but also put continuous load on your source systems. So usually we run this overnight, and nightly batches are easier on system, but it means that your data warehouse is always a day behind. And then how to capture? So push means that the source system notifies you when data changes, so near real time, but it requires source system configuration. Pull means that your ETL job reaches out on a schedule. It's simpler, but you only get updates when you ask. And that's a full versus incremental extraction. Do you pull data every time or just when changed? Incremental is more efficient, but also more complex. And we also need to decide the frequency of data extraction and the latency. And there is always a trade-off between the two. So if extraction is gathering ingredients, cleansing is quality inspection. The goal here is we don't want to let bad data contaminate our data warehouse. Because once the bad data is there, it spreads. So bad data can really lead to bad reports and lead to bad decisions. So first, we have to find the problem. We have to run the validation rules, and we have to generate exception reports. We need to eliminate incorrectness, and we need to enforce integrity rules. Then we need to decide how to handle each issue. So some of those we can fix. Some of them we have to filter for manual reviews, and some of those incorrections we just have to remove them. But here's what separates good data team from great ones, which is prevention. So when you keep seeing the same issue, you need to work with the source system owners to fix the root cause. So stop bad data from being created in the first place. So some of the example bad data are misspelled names or places or addresses, then some impossible values. So birthday of February 30th or order placed in 2099 or negative quantity on hand. Okay. And then we also have logical inconsistencies, duplicates. And here is the important principle. So data quality is contextual. Good enough depends on what you are using the data for. Now let's move to data transformation. So data transformation is where you turn raw, cleaned data into something useful for analysis. The key insight here is the source system captures the data for operational services. The data warehouse really need to store data for analytical purposes. So different goals requires different structures. The integration here means that we combine data from multiple sources into coherent records. Customer exists in CRM, billing address, and support system, and we need to transform one unified customer record. And granularity change means adjusting the detail level. Operational system captures every transaction, but analysts typically want daily summaries, weekly totals, or monthly trends. Then we have data quality assurance, and last we have data enrichment. This means that we calculate the new values, customer age from birth date, physical quarter from transaction dates, profit margin from revenue minus cost. Think of this as cooking. Extraction gather your ingredient, cleansing washes and inspect them. Now transformation is actual cooking. We combine them, reduce them, and we present them. So let's get a little bit more specific about transaction functions. The golden rule here, we want to work backward from how the data will be used. What questions will analysts ask? What dimensions will they filter by? And the record level transformation works on entire rows. Here we have selection that filters which record to include, and we have the joining combination, which combines records from different tables. Operational database are normalized. But for analysis, we sometimes want everything together, so we need to denormalize the tables sometimes. We also have field level transformation that works on individual columns, and this involves single field transformation, which transforms one column to another, for example, converting the units, translating codes. And we also have multi-field transformation, which combines multiple existing columns into one new column. And I will show you some examples. So single field transformation are building blocks. An example is temperature convention. So US facilities report in Fahrenheit, European facilities report in Celsius. You can't analyze them together until they are in the same unit. So we need to pick a standard, Celsius, and transform. And this is exactly like currency conversion. We can't add dollars and euros without converting them first. Then we also have code lookup. So that in the source system often use codes for efficiency. States may be coded as CA instead of California. And status may be coded as 1 or 2 instead of active or inactive. But business users don't want to decide what status equal to means, right? So transformation looks up the code and translates into human readable value. This transformation may seem trivial individually, but hundreds of fields across dozens of systems, it adds up very fast. Multi-field transformation are more sophisticated, splitting one field into multiple or maybe combining multiple fields into one. So in this example, the source system stores product code, for example, Nike Air Max, as a single field, which is efficient for inventory. But the marketing wants to analyze by brand. How is Nike performing versus Adidas? With combined field, that query is awkward. So during the transformation, you split it into two fields, brand name and product name. So now the analyst can filter by brand, aggregate by brand, and compare brands. Think of this as unwrapping a package. The source system handed you information bundle for the convenience. Now the transformation will unpack it for the analyst's convenience. The key principle here is operation systems optimize for capturing transactions, but analytical systems should optimize for answering questions. So the transformation bridges that gap. The last step is loading and populating. This may sound easy. We just move the transformed data into the warehouse. But there are some real considerations. So the timing really matters. So loading takes resources. So schedule during off hours. And also the volume matters. Load millions of records. Think about bulk loading utilities, parallelism, and partitioning. And also, how do we handle failures? That really matters. What if the load crashes halfway through? Can you resume from where you left off? And indexing also matters a lot. After loading, we need to create indexes for faster queries, but indexes slow down the loading. There's a trade-off there. So if ETL fails and isn't fixed by morning, analysts can't run reports. Dashboard shows old data and decisions get delayed. Now the characteristics of data after ETL. When ETL is done well, what do you end up with? We have appropriate granularity, the data at the level of detail users truly need. We have historical depth, and we have customer records, have their purchase history, support tickets, campaign responses, permit payment history, all integrated. We have optimized structure. Data may be denormalized, but we are trading redundancy for query speed. We also have freshness appropriate to need, not real time, but current enough. We also have quality that you can trust, and this is validated. So when the CFO present number to the board, they can trust those numbers. So this is ETL's promise, one source of truth, optimized for analysis. Some people talk about transient data versus periodical data, and this is one of the most important distinctions, the difference between how operational and analytical systems handle data over time. So transient data only keeps current state. When a customer changes their address, the old address will get overwritten. So the system knows what's true right now, but it has no idea what was true yesterday. Think of this as a whiteboard. You write today's information. Tomorrow, you erase it and you write new information. The old is gone forever. On the other side, periodical data keeps history. When something changes, you don't overwrite. You add a new record with a timestamp. Customer change addresses on March 15th. Keep the old records. Add a new record with March 15th as the effective date. Think of this as an accounting ledger. Every entry is permanent. You can always see what the book looked like at a point in time. So why does this matter? Because analysis often requires historical comparison. So how have sales changes over the years? And what is the churn rate last quarter versus this quarter? All of these need historical data. If you've taken a database course, you learn about normalization, eliminate redundancy, organizing data into clean tables with proper relationships. But then when you get to data warehousing and we say actually denormalize. So what's going on? Normalized data is optimized for data integrity. So the category table I have here have each category once, and then the subcategory table will reference the category through a foreign key. But now, what if I want to rename furniture to home and office? We change one record, very clean. But to get subcategories with category names, we need a join. Every query does extra work. But now, if we are going to denormalize data, and here we are trading redundancy for performance, the category name is stored physically in every subcategory record. Redundant? Yes, but query don't need to join. And we can easily filter by category, and we can easily do aggregation analysis by category. So why the difference? In operational system, in the traditional database, they are optimized for transactions. We have lots of small reads and writes, so normalization prevent anonymous. But in analytical system, data warehouse, here we are trying to optimize for queries. And then we have large reads, we have very rare writes, so the speed really matters more than update efficiency. So in data warehouse, we accept redundancy to get faster queries. Alright, so now we have covered ETL, which is a heavyweight champion. Now let's meet the challenger, which is data virtualization. Data virtualization represents a fundamentally different philosophy. Rather than physically moving data, you create a logical layer that provides unified access to data where it lives. The data stays in the source systems. We're just creating an abstraction. The virtualization tools has connectors to various sources. These can be SQL databases, APIs, cloud services, spreadsheets. And a business user builds a visual workflow defining what data they need and how to combine it. The tool generates a virtual table that looks like a real database table, but behind the scene is querying multiple sources on demand. So data stays put, nothing moves. The real time by default, when you query the virtual table, you are querying the current source data. And transformation happens on the fly. The tool will convert, combine, and calculate as queries run. The mental shift here is that while ETL says bring the data to the analysis, virtualization says that bring the analysis to the data. So now let's walk through the architecture. At the bottom, we have the data sources, the ERP systems, Excel spreadsheets, database, and XML files, etc. Then we have the connectivity layer, which provides the bridges. So here we have the SQL connection, ODBC drivers, APIs. And then in the middle, we have the Mashup tools. And the workflow is user-defined process. So what data do I need from which sources? How do I combine them? These are typically visual tools, and you can drag and drop. And then we have the query engine, and which figures out the optimal way to retrieve the data from the sources, applies transformation, and combine the results. Then we have the virtual table, which presents the unified view. At the top, we have the user, and the user will only see the unified data. They may not even know their query is hitting 5 different systems behind the scenes. So the key emphasis here is user-friendly interface. This is designed for business users, not for IT, and that's a self-service promise. In recent years, the market has exploded with many different options. There are enterprise-level options, such as typical SAP HANA. And then there's also analytics focus, like Alteryx, Tableau Prep. And then we also have very specialized platform. Which one is right depends on your needs and your existing infrastructure, expertise, and as well as a budget. The good news here is the concepts transfer. So once you understand how virtualization works and their principles, picking up any specific tool is pretty straightforward. Let's talk about the benefits and the limitations of data virtualization. So first, you have self-service. Business users can combine data without waiting for IT intervention. And then speed to value, 1 week versus 8 weeks for ETL. The real-time data, no batch delays. There's also no storage duplications, so data stays in source systems. Then it's a very agile approach, very easy to implement and easy to experiment. There's also low cost. It's generally much cheaper than traditional ETL. In the meantime, there are also a few drawbacks. The performance impact. Complex queries hit source systems directly. To run heavy analytics during peak hours, you might slow down operations. Source knowledge also required. Users need to understand the source data structures. The governance challenges. So when anyone can create a virtual view, how do you ensure consistency? It also requires change management. When source systems change, who to update the dependent views. Virtualization is powerful, but not magic. It works best with the appropriate governance. To summarize, let's put ETL and data virtualization side by side. So data location, ETL creates a new physical store, but virtualization keeps the data in places. Data movement, ETL requires move data in batches. Virtualization does not move data. Data freshness, ETL has some latency, but virtualization is real-time. Best business use cases, ETL is for large-scale historical analysis. Virtualization is for quick, flexible reporting. Performance impact, ETL has minimum impact during operations, but virtualization can burden sources with every query. The setup time, ETL takes 8 weeks, virtualization takes only 1 week. So what is the answer between the two? Usually both. We use ETL to build your foundation, the warehouse powering standardized reports, historical analysis. We use virtualization for agility, ad hoc questions, quick experiments, real-time dashboards. The best architecture are hybrid. Before wrapping up, let me bring you back to where we started. Hershey Company eventually recovered. It took time. They had to slow down, test properly, get the integration right, but eventually they realized the benefits. But that Halloween of 1999, empty shelves, $100 million lost, competitors grabbing market share, all because the systems could not talk to each other. It didn't have to happen. If they've integrated properly, tested thoroughly, planned realistically, they would have shipped every Reese cap and Hershey Kisses. So data integration isn't glamorous. It's not the flashy AI model or the beautiful dashboards. It's plumbing, foundation, infrastructure that makes everything else possible. Without data integration, you're building on sand. Or worse, you're sitting on a warehouse full of candy you cannot ship. To summarize, we have learned why integration matters. We defined integration and their approaches. We dived deep on ETL, and we also explored virtualization. We learned that the best answer is usually both of them, ETL for your stable foundation, virtualization for the agile layer. So remember, the question is not if you will need data integration, it's when and how. So that wraps up this data integration lecture. Thank you for watching.